Jacobi method. And let's see, what do we have here? So let's see. And then we have this. Okay, good. This is the stuff. Let me see. This is Jacobi's method. And we derive the, let's see. This is the Jacobi's method. And we update it with all the things is on the right hand side are k minus 1, and now on the left hand side we have the k step, the k vectors on the left. And we also point out that, okay, we write out the things here, and then from the very first equation in the Jacobi's methods, and then we calculate the first component in the k vector, and then we know the first components for the k vector now, and we make use of this value, and then instead of using the k minus 1 value, and then we are going to change these to the k values first, k iterations value, and then first components value. And we would do this for all these formulas here, and then the things below the diagonal, although the diagonal are weakened here, we don't have anything on the diagonal, and then but below the diagonal, and then we are going to change every superscript here, and then from the k minus 1, and then we change it to k, and which means that we are making use of the k iterations result, and then to update the values here, the n component here. So this is just one small change from the Jacobi's method, and then this part is still Jacobi's methods. And let me circle it out. And this one is the Jacobi's method. This is still the Jacobi's methods part. And I upgrade the method, and then with the updated value in the vector k. And so this is this part, and then this is the purple part, and then this is the Gauss-Seidel method. And as you can compare to what we have above, and then we just change the superscript here, and then from k minus 1 to the k, and then which means that, okay, this is the updated message in the formulas. And this is the Gauss-Seidel method. And Gauss-Seidel method. Gauss-Seidel method. Seidel method. And this is the Gauss-Seidel method. And if I want to write down the formula, all this system of the equation here, system of the formula here into one expression, and then I can write it in this way. So, and I'm just copying down this formula first because it's just one small change. So that's this one. Because if you take a look, observe these formulas we have here, and then before the diagonal, and then which means that before their index I, and then the things are here. Let's say this is the positions I position on the diagonal, and then before the index I, and then we have the superscript k. And then up to the diagonal, and then we have things coming from the k minus 1. So instead of having only the k minus 1 here, then we are going to split the items, and then before the I index, and then after the I index. So here the formula becomes to let's see. In case I write something wrong, and then I should also have the notes here. So I'm going to write the things
before the index I and then after the index I. After the index I is still from the k minus 1. So let's see. After the index I, so after the index I, we have the J index is from, I saw something wrong in the very beginning, at the very beginning. And then this one, it should be XJ. Here we have XJ as well. And then here the J should starting from, because it's after the index I, so here it should starting from I plus 1. And before the index I, and then what do we have? And then we have something, and then that is from the J equals to 1 to the something in front of the item in front of, right in front of the index I item. So here it should be J equals to 1 to I minus 1, and Aij, and then Xj, and then now the things in front of the index I, and then they are from the K vector. So we have the superscript K here, and this is the Gauss-Seidel formula, and all things in one formula. And this is the I equals to 1, 2, and then to the n, because we have n component here to calculate for the K vector. So this is the things, and then let's just do one example for this. I'm going to use the same examples as the Jacobi's method. Let's see. Let's just do some copy and paste here. So let's see. And actually, we still need to show for the so this is the same example we are going to use. Let me just write down here first. So for this one, for the examples we have here, for this example 2, and then we are using the Jacobi's method. And now we are solving the same system of the equation, but we are using the Gauss-Seidel method. So let's see example 3. And we are using with the Gauss-Seidel method. And what should we do here? So first of all, you still need to do the step 1 and then solve for the xi from the EI equation. And the next we are going to, so this is the first step, and then you're doing the same thing in the Jacobi's methods. And we solve for the xi, and then with the equation ci. And now this is the diagonal, and then below the diagonal, and then we give the superscript k, and above the diagonal, and then we give the superscript k minus 1. And on the left-hand side, and then we would keep it to k superscript. So here we have the formula for this system of equation, and it should be, so let me just copy them, and this equation first, and then I will give the index for this number that is corresponding to the Gauss-Seidel method. So on the left, and then they are just from the K. This is the things we want to calculate for each step, and then below the diagonal is here, diagonal here, and and this is just the last column, and then this is just the constant vector, the B vector here. or the C vector here, the C vector in the matrix format. And so the diagonal part of the purple part is the purple part. And then so below the diagonal, and then we give the superscript K. Superscript K here, superscript K here, superscript K here, superscript K here. And then above the diagonal, we are giving the K minus 1, K minus 1, K minus 1. All the things are K minus 1, but we don't need to do anything for the constant item. And so this is the things you want. Well, this is with the Gauss. This is the Gauss-Seidel method, not Gauss-Seidel, sorry. Gauss-Seidel. We don't make any guess here. Gauss-Seidel method. Okay, this is the formula. And then you have already finished almost 50% here. And then the next thing is to do some calculation. And then once again, we start from the initial point. The initial vector is 0 vector. And we begin with the 0 vector. And then so now we have the x1. That's super interesting because if you see something here, let's do some calculation. Okay, good. And we have when we have the x0 vector, and this is the x0 vector, and then the initial vector, and then this is the 0, 0, 0 transpose, and because we need the column vector. And what is the x1, 1? So we are calculating the x1 vector. So this is already step 3, and then let us compute the vector in the first iteration, and then that is C. So x1, the first component for the vector 1, and then we have it equals to so we have the 0 vector, and then times 0, and then minus 1/5 0, and then plus 3/5, and this is just 3/5, and it's around 0.6000. And now for the x2, 1, and then we follow the formula here, and I just copy down all the things here in case you don't understand what I'm doing. So I just copy and paste and then replace the number there. And I don't need the color. Thank you. Okay, good. And x1, 1, and then but we are doing the we are calculating the 1, and then the k index here is 1. So here we have 1 here, and then here is k minus 1. So this one is 0, and then this one is also 0. And so now what you have for the x11, you replace the number here with 0.600. And this one, if you look at the number here, you look at the x0 vector here, and you will see the x30, x3, okay, the x30 here is the third component, and then it's 0. It's the 4th component from the 0 vector, and then it's 0. So we have 0 here. We have 0 here. So at the end of the day, you use the number we have, and then you can use a calculator and then calculate the number. And at the end of the day, you would get something, and you do some rounding here. Of course, this is divided. It's dividing number 11, and then I believe you should do some rounding off here, and then let's keep 4 decimal places. And for the x31, we are going to copy all the things here, x31 and the x41, and then we would do the calculations at 1 at one time. And then here we have all the things here. I don't need the color. Okay, so on the left hand side is still is the first situation. So it's 1, and then it's 1, and then the K here is still 1, and this is the K. So it's the first iterations, result, first iteration result. And then for the K minus 1, and then it's just 0. So here, right now, you already get x11, and x11 is from, x11 is from here. You can see x11, we just calculate the x11 in the first part, and then x21 is from the second part. So I'm going to replace this value with, and then this one is just equals to 0.6000, and this one is just 2.3272. And what's x4? 4 is the fourth component from the zero vector, the initial vector. So this one is 0. And let's see, x2, 1, and then this one is from the second equation, and this one is just the 2.3272. And this part is just, I haven't calculated yet, sorry. I should do the plugin here and then calculate the number, and then I find something missing here. So now you can see we should do step by step, because we need the number from some things here. So we need to calculate one by one. We cannot do at one time. But the Jacobi methods can do it at one time, but Jacobi methods is not as good as we have here for the Gaussian method. So we prefer the Gaussian method. And then this one, if you do the calculations in the calculator, this is approximate this number. And then now we have the number, we are happy. Let's do the plotting here. This is negative 0.9873, and then you can plug in, and then do the calculation. And at the end of it, you would get a number from the calculator, and then that is the 0.8789. Is it easy? No, not too complicated. And then you need to do it one by one, and then you see the things just happen. And then I want to calculate the x3 and then x4 at one time, and then it doesn't work, and then because I need the result from here to put in here. That's the Gauss-Seidel method. You need to calculate one by one. And let's see. I'm not showing you more iterations by hand, but let's see. Let's take a look at some numerical result, which means that you can go to play around with the code I posted on the canvas. I hope you notice that I have a code section there. Although I don't require you to know how to do the coding, the actual coding, but it's really good to know how the coding works for these methods I claimed in the class. So, you know, there's a computer program here. Maybe it's created by the AI. And now let's see some numerical result. So each time when we talk about the numerical methods, and now most of the time we should involve the, let me see, this part should be the SOR and the iteration methods. Let me see the numerical methods here. No 4B. Iteration. Okay, we got this. So for each numerical method, and then we usually have, and especially for this iteration methods, and then we have the stopping criterion. And I mention the stopping criterion here before? And but for this question, the stopping criterion is so for the choose numerical method, and then you do the algorithm, and then you have one stopping criterion: stop the iteration, stop the for loop, stop the while loop. You have the while loop, why the number something k is smaller than this, and then we would do these things. But once the k is bigger than something, and then we stop doing the while loop or for loop, right? And this is the while loop and for loop, and then you have a stopping criterion there. For this question, and then actually in the question statement, and then it has a stopping criterion here, stopping criterion. And then it's the relative difference, k here, k minus 1 here, and infinity, and xk, infinity, and smaller than 10 negative 3. I remember that I have tell you why we have this kind of stopping criterion here, because if this method work, and then this is a convergent sequence, and then because it's a convergent sequence, and then it is a Cauchy sequence, and then which means that any arbitrary item up to one point, and then their difference are small. And so here we check this stopping criterion here. Let's see, we have something here. This is a Gauss-Seidel method, and let me get the numerical result here. We actually have this. This is a numerical method. If you run the program, and then it will stop at one point, and then it will stop at the 5 iterations, the 5th iterations result. And this is the component value, and then this is the initial vector. We have just 4 components here for one vector, because it's a 4-dimensional, it's a 4-dimensional space. And then this is the first iteration result. This is the x1. This is the x2, and then this is the x3 vector. This is x4 vector, x5 vector. And if you run the program, and then it will stop at this point, because if you check the stopping criterion here, and the relative difference between 2 iterations is quite small, and it's around 4 times 10 to the negative 4, which is smaller than the 10 negative 3 we choose there. There's the Torrance number there. So we view this x5 and as acceptable approximations to the solution, because it satisfies the stopping criterion there. And this is the things. And if you want to compare this with the Jacobi's method, and then let's go back to the Jacobi's method. We also have the numerical result there. And the numerical results, let's see. We should have the numerical result here. This is the same problem. We are solving the same linear system equation, and then with the same complex number, 10 to the negative 3. But here, this is the Jacobi's method. And then this Jacobi's method, it requires 10 iterations to solve the iteration. And which means that it requires 10 iterations to satisfy such a stopping criterion. Which means that if you compare to what we have in the Gauss-Seidel method, we just need 5 iterations. And in this way, from these examples, you can see that the Gauss-Seidel method is actually working better, because it is converged. Oh, just astonished! What beautiful sound. Okay. So
this Gauss-Seidel mapper is converging faster than the Jacobi's mapper. And that's why people would choose this rather than choose the Jacobi. So Gauss is a very great mathematician, greater than Jacobi. Just kidding. They have their, they are in different times, right? And then maybe Gaussian's mappers is based on Jacobi's mappers. Yeah, of course. And then someone invented something and then they just doing some improve it, right? Not a greater mathematicians. We cannot compare in this way. Yeah, and so let's see. Do we have the matrix format for this one? Yes, of course, we can have the matrix format. And how do we get to the matrix format? And we can do it in this way. Let's just do the things in this way, and let's write down the k things on the left, and then write down the k minus things on the right, and then that's the equations we have it here, and then so this is the Gaussian-Seidel methods and matrix format, and then we want to write down the matrix format because I said before, and the matrix format is very important to investigate the convergence of the methods. And so now let's write down the very first equation, and then I put the things on the left, and then that's from the k iteration. It result, and then from the right, and then we have the k minus 1 things on the right, but this is corresponding to the Gaussian-Seidel mapper. So on the left is sometimes in front of or into the index I, and then on the right is sometimes after the index I. That is the diagonal items. And here we have n k minus 1, and then plus the b1. And what we have in the second one, and then we have a21. We also want to include the diagonal, and then that is x2k, and then equals to, so we already have a22 here on the x2 is on the left, so we begin with the x3 here. So a23 x3 k minus 1 k minus 1, and then we have the x2n and then k minus 1, and then this is a second equation, b2. And actually you have more equations after it, and then we have n equations in total. And at the end you will have an1 x1k, a2n, an2 x2k, and then let me see, we should have up to k and n minus 1, because we from the previous equations we get the n minus 1's number, x n minus 1 and then k. Am I right? No, we should include the diagonal. It should be ANN, sorry. Because this is just a variant format of this one. This is just a variant format of this one. And then we would have the AII XIK here. So we have X and K at the end. Okay, on the left, we only have, that's the only item here, BN. And as you can see on the left, for the coefficients matrix, it's actually the lower left matrix with the diagonal. And we can express it in this way. D is the diagonal, and then plus the L is the lower triangular format, this lower triangular matrix without the diagonal. And it's multiplying in the xk vector. This makes sense. This is the matrix format for the left-hand side item.
And if you cannot understand this, and then just skip it. You don't need to understand this whole things. And then just memorize the formula at the end. I know some people are not very good at the linear algebra. I can understand that, because I'm not very good at the linear algebra as well when I was like freshman year student or second year student. And so I'm going back to here to let you see something. I will let you see the definition in case you forget the definitions of the D and L and U. And then I'm going to scroll up to let you to take a look at the definition here. D is the diagonal, and then L is the lower triangular part, and then excluding the diagonal part here. U is the upper right triangular part, and then with the zeros in that diagonal. And this is the compositions of the A. So here we have the D plus L, and then because we have a lower triangular matrix, and then with the diagonal. So here this is just the diagonal part, diagonal matrix, and then plus the L, lower triangular matrix part, and then with the zero on the diagonal here for the L. So this is the left-hand side part, and then for the right-hand side part, there is two parts here. You will see there's a constant vector here. This is the first part, and then the second part you have is an upper right triangular part. And because we don't have the x1 item here, we don't have x2 item here, we don't have xn item here, which means that this is an upper right triangular part, but without your diagonal element there, non-zero diagonal. So here, this is the zero diagonal, and then with the upper right triangular part of from the A matrix, and then this is the U matrix, U, and then times, because this is the k minus 1 iterations results on the right hand side, and then we have the x k minus 1 vector, and then plus b vector, the b vector b1, b2, and the bn. So now, the question is that, let's write out the iterations formula. The iterations formula for here, you will see this is the iteration formula. Xik equals to something's on the right hand side, and I'm going to also write the matrix format in this way. Xik and equals to something, and but the things for the xik, you will see for this component-wise formula, and then the xik on the right-hand side are from the lower left part, from the lower was the lower left part coefficients. That is the L coefficients there. So let's see, we would have, I'm going to do some subtraction here actually. Let me see. Actually, I don't know. I believe I can write it into this way. Xk, and then let's see. Just do the inverse. D plus L inverse. And then U, and then xk minus 1. And actually it includes all the things we have. D plus L, and then inverse, B inverse. B vector. And this is the matrix format for the Gauss-Seidel method. Although you have see, this is kind of something different from the component-wise methods, the formula. Component-wise formula, and then we have the K something on the right. But here, if we write it into the simple and then clear way in the matrix format, and then we just have the k minus 1 things on the right hand side, and then with the matrix multiplication here. And once again, we give it the name, and then give it some notation here. And this one we call it to be the T matrix G, and then subscript with G. And this one we give it a notation here, C, and then with the subscript G, and then which means Gaussian. Gauss-Seidel. And here we can write the iterations. This is the matrix format. And then, so here we can write it into xk, and then equals to tg, and then k minus 1, and then plus the cg. Yes, that's it. And then the tg equals to this d plus l inverse u, and then cg equals to the d plus l inverse. And this is the things. Let me see. Actually, we have something here. Should we calculate? Should I give you one example how to calculate this matrix? Let me see. Is it a good example here? This is the L plus U. So I'm not going to give you one example to calculate this matrix here. And I'm going to move to the convergence result part. So if you, I believe this matters, and then you just need to plug in the d plus l, and then doing the inversion and multiply by the u, and then you will get the T matrix. And then just follow the formula here, and then to get the T matrix, and then C vectors for a special example. And I'm not going to give you one numeric example here. Now let's go to take a look at the convergence results. Convergence results for the iterations method. And the general iterations method is xk, and as you can see here, xk, and then there's a multiplications matrix here, and then xk minus 1, and then there's a vector here, c. And actually, there's a theorem stating that about the convergence result. So the theorem is stating that, so for any, you will see this, you don't have any restrictions on the initials vector. You can choose your own initials vector, and the sequence generated by the rule above, the sequence defined by, so this is the vector sequence, and then the vector sequence is generated by, it's defined by this, defined by xk, and then equals to t, xk minus 1, and then plus c. Then we have convergence, convergence to the unique solution. And it's actually converge if you let the things to converge, and you have these things converge to one vector, and then this one is in the same sequence. So if this sequence conversion, and this is going to the same vector, right? Because let's assume that it converged, and then the left-hand side is converged to one vector, and then on the right-hand side, the xk minus 1 is going to the same vector. So let's say that vector is x. So on the left-hand side, you have, if you take the limit, let the k tends to infinity, and then this would go to x, and then this would go to x as well. So it would converge to the unique solution here, and then the unique solution is x equals to tx plus c. And you will later on learn this again, but it's in the one-dimensional space. And that is the fixed point method. And this is just the fixed vector here. But here the things is convergent, and then if and only if there's one criterion here, and then it's all about the T matrix. and it's about the spectral radius of the T matrix, and it should be 1. And I know a lot of you are wondering what is the rho T, and then I said this is the spectral radius. Spectral radius of T. And the spectral radius of the T is divided by, it's kind of something's related to the norm of the matrix A. So I'm going to give you one example here. Oh. Do you know what is an eigenvalue of a matrix? Raise your hand if you know what is the eigenvalue of a matrix. Okay, so most of you know the eigenvalue of the matrix, so I'm not going to introduce the eigenvalue again. And so the radius, the spectral radius, definitions of spectral radius. And then it's just the, so this is rho is the spectral radius notation. And then, so let's say this is the spectral radius of the A matrix, matrix A. And the spectral radius of A is just the maximum of the magnitude of the eigenvalue, where the lambda is an eigenvalue of the matrix A. And usually you have like, so if an A matrix is an n by n matrix, and then you will have n eigenvalue, right? And then, so for example, this is A is an n by n matrix. And then actually you would have how many? You would have, let's say we also count the repeated eigenvalue here, and then you would have n eigenvalues. And you will have lambda 1, and then lambda 2, and then to the lambda n. And then the rho A is just the maximums among the lambda 1, lambda 2, lambda n. But taking the magnitude or the absolute value here, because the eigenvalue could be complex number sometimes. It depends on the matrix you have. And so this is the things. And so let's see, I'm going to compute one more things. So I should also point out that this side, if this is a complex number, if lambda is complex number, and then the absolute value side, or this is not absolute value side, and then this should be the magnitude of the lambda, the complex number. If this is a complex number, and then the lambda magnitude is defined in this way. So let's express the lambda, this complex numbers in this way. The alpha, and then plus the complex part, and then that's beta I. And then now the magnitude lambda, and then it's defined with alpha squared plus beta squared, and then divided by and doing the square root. And this is something's covered in the complex analysis class or some basic calculus class. So next time I'm going to give you one example, and then I would do the calculation here, and then to calculate the matrix A, and then for this is the matrix A, and then I will teach you how to calculate the rho A here. That is the spectral radius here for this specific example. And you can also try to practice the concepts on these examples beforehand. And the next time I will show you the solution, how to do the actual calculation. And that's all the things we want to cover today. And then if you have any question, then please come over to here. And if you miss the deadline to submit the correction, and then please send an email to me, and then I can give you some extension.
你把周一的那个 recording 发给我。
啊，周一啊，
我没录上了。
没录上。
那怎么办？
我去看看以前的有没有。
哦，
吧
我有事儿，那我没来。
我知道，我没录上，我知道，但是
你今天录了是吧？
应该有吧，希望有吧，有啊，
有吗？
有。